So, more than inviscid flow, we also required the flow to be incompressible. We required uniform approach flow. You have a zone of disturbance, which is a solid object usually, and flow going past the object, which is equivalent to object going past a stationary fluid at a given speed. Under these conditions, so because of incompressibility, del dot u is 0, and because of uniform approach flow, we found del cross u 0, which is equivalent to vorticity 0, and vorticity is at least a measure of rotation of a fluid element, and because of the word rotation, and that is 0, which makes the flow irrotational. So, these terms are interchangeably used. Now, since del cross u is 0, u should be expressible as the gradient of a scalar potential. This will identically satisfy this equation del cross u equal to 0. Of course, phi at the moment is unspecified, it is some function phi, but the fact that such a function exists whose gradient is the velocity field leads us to what is called potential theory. It also suggests that we find phi, find u, and pressure from Bernoulli's equation, followed by forces and moments. So, this now becomes our analysis approach. When you solve this problem, effectively you will get the solution of Euler equations. Those are Navier-Stokes equations without the viscosity terms. So, now u is equal to gradient of phi, substituting in the mass balance equation, you get a single equation for phi. You can't, so u equal to gradient of phi can be used to find u, but first you have to find phi. So, substitute that. So, when you solve for del square phi equal to 0, you are satisfying mass balance and you are also satisfying the irrotationality condition. Both are being satisfied. So, essentially you have to solve Laplace equation for phi. And I was telling you that books like Kreyszig will give you many techniques for solving such equations. Rather than dwell on those techniques, the approach we will adopt is look at some solutions and examine the geometries that they represent. So, the hardest step in this development is solving this Laplace equation for the velocity potential. So, once you get phi, so this will be along with boundary conditions. So, once you find phi, you can find the Cartesian, let us say Cartesian coordinates. This is u and v are the Cartesian components of velocity. Sometimes we work in polar coordinates. Then you have so the polar coordinates are also defined in the xy plane, and you know the connection between r theta on one hand and xy on the other. Using components, you can also map u r u theta, the velocity components, to Cartesian u and v. So, since u is equal to gradient of phi, u is the x derivative of phi, v is the y derivative. Similarly, the radial velocity is the r derivative of phi, and the tangential velocity is the theta derivative of phi. Now, you also know that if del dot u is 0, then a stream function will exist. Okay, so, we had defined u as this is also equal to psi y, the derivative of psi with y. This is equal to minus psi x. So, where I think I did not write this, phi is a potential because derivative of phi is velocity. So, phi is called velocity potential, and psi is the stream function. So, if you start with psi, the mass balance equation is automatically satisfied, and then you can substitute in this omega equal to 0, and you will find that del square psi is also 0. So, both phi and psi are valid potentials of the flow field. You can choose one or the other. So, in this course we will opt for velocity potential for no specific reason. It could be A or B. So, A or B meaning phi or psi. But you can go from phi to psi. See, when you want to visualize the flow field, it is psi that helps you, because a constant psi line is a streamline, and you know flow is going along this streamline. So, for visualization we prefer to use psi. So, you would like to know how do I go from phi to psi. So, here you can see, if you just look at this block, it tells you how to go from phi to psi. Okay. So, if you know phi, find the x derivative, then integrate this equation, partial derivative of psi with y is phi x, that will give you psi with a constant of integration that depends on x, and then use the next equation to find the constant of integration. Similarly, you can do it in polar coordinates. So, this is equal to 1 over r psi theta, and u theta is minus psi r. Okay. So, You can do it in Cartesian or in polar coordinates. So, this the central idea behind solving del square phi equal to 0, unlike separation of variables, that was one approach. The other approach commonly used here is called the method of potentials. Here the strategy is build a library of functions that satisfy del square phi equal to 0. There are millions of such functions that satisfy del square phi equal to 0. Then do a linear superposition of some of them and determine the constants in such a way that boundary conditions are accounted for. So, this is the approach, but then we are not going to follow that approach. I will give you the solution and then we will explore what it stands for. Last time I gave you this potential and we found that u is equal to capital U, v is equal to 0, which is just uniform flow along the x direction. U is the x velocity. So, using phi x equal to psi y, you get u equal to psi y. So, integrating it is u y plus f x and then minus psi x is minus f prime, which is 0. So, f is equal to just some constant, neither a function of x or y. So, that gives you psi. You might know from your previous courses that potentials are determinable only up to an arbitrary constant, and then the constant, by relating it to the geometry, you can fix the constant. So, here also you can fix the constant by saying that psi will be a stream 0 streamline on y equal to 0. If you say y equal to 0, psi equal to 0. So, y equal to 0 is x axis is the 0 streamline. If you prescribe that, constant of integration is also 0. So, you can see that from phi we have been able to find psi. So, this problem can become much harder when the function phi is more elaborate. Okay. But this solution, see, y equal to 0 gives you a streamline. So, let us say this is the x axis and it is a streamline, that means flow is going along this line, which is just a, well, the flow normal to it is 0. So, you can say that flow over a flat plate is given by the velocity potential phi equal to u x. And look at the constant phi lines, those are x equal to constant, those are vertical lines. And you can see that the constant psi lines and constant phi lines are orthogonal in this example, but in general they are orthogonal. If you, how do you get the constant phi and psi lines? So, suppose this is on phi equal to constant, d phi is 0, which is phi x dx plus phi y dy. So, dy dx, the slope of the constant phi line is phi x, this is minus u over v. Similarly, on a streamline, dy dx on a streamline is equal to plus v over u, okay, which is the slope of the velocity vector, and the product of the two is -1. Therefore, constant phi lines and constant psi lines are orthogonal. So, this the fact that you can get phi from psi, psi from phi, and they form an orthogonal grid, these are all very helpful in visualizing the flow field. So, we looked at another example last time. So, what does this potential represent? So, to visualize this function, we first find the velocity components. U r is the partial derivative of phi with r, which is u 1 minus r square over small r square cos theta. U theta is equal to 1 over r phi theta, which is u 1 plus with a negative sign, cos theta becomes minus sin theta. These are the velocity components. As r is the position from the location from the origin. As r approaches infinity, u r and u theta will approach u cos theta and minus u sin theta, respectively, which is uniform flow, right. U r u theta approaching u cos theta sin theta represents uniform flow. If this is the flow field, these are the velocity components in r and theta directions. So, far away from the origin, and origin is where we propose to disturb the flow. Second is in the vicinity of the origin. So, that would be r equal to capital R. U r, that is the radial velocity, is 0, okay, and u theta is equal to minus 2 u sin theta. Now, r equal to capital R represents a circle in the xy plane. So, the and the normal velocity on that circle is 0. So, it represents a streamline, therefore, it is an object. So, this potential represents flow past a circular cylinder of radius r. Okay. So, having established the velocity components, you can also see that u theta happens to be 0 at two specific points let us call them A and B. So, at points A and B, theta is either 0 or pi and u theta is also 0. So, these points are called stagnation points. These points are special because if velocity is 0, your Bernoulli's equation tells you that the pressure has to be a maximum. Okay. In the flow field, whenever you have a stagnation point, pressure will hit a maximum, because P over rho plus u square over 2 is a constant. So, applying Bernoulli's equation, at any point in the flow field, so this will help you find pressure anywhere. But in the class of problems we are looking at, the force acting on the object is most important. Therefore, we need pressure acting on the surface of the object. So, on the surface of the object, which is u r is 0 and u theta was minus 2 u sin theta, which makes it 4 u square sin square theta divided by 2. This will be equal to, the constant is evaluated under upstream conditions, the undisturbed or far field condition. Can you think of it as far field or upstream? Upstream there is some pressure. Now, you may call it reference pressure. Okay. If you have an object moving in air, then locally there is an atmospheric pressure. So, that would then be the reference pressure. So, some authors, offhand I do not remember the notation used by Frank White. Sometimes the symbol infinity is also used, P infinity. P infinity is far field, and it does not mean light years away. It just means away from the zone of disturbance. This is P infinity over rho plus the velocity there is capital U square over 2. So, P minus, so I should write P just to be specific. So, this I am expressing it in dimensionless form. So, rho was already there and half u square was on the right hand side, I am pulling it to the left. So, now left hand side is a dimensionless pressure distribution. Why distribution? Because it is a function of theta. Is equal to 1 minus 4 sin square theta. And you can get the forces. Forces are obtained by integrating stresses on the surface of the object. There are normal stresses and shear stresses. Shear stresses are 0 because viscosity is 0. Only normal stresses, which at the wall will become equal to pressure in terms of magnitude. So, the x component force, if you wish, you can show a portion of the cylinder, and this is the direction of P. So, the x component force is minus 0 to 2 pi p r theta cos theta, this is the x component r d theta, and y is 0 to 2 pi Now, what is this p r theta? You can substitute 1 minus 4 sin square theta and get the results in dimensionless form. Now, a very unusual result that comes out of this analysis, this potential flow analysis, which looks very interesting, but ultimately if you evaluate these integrals, they turn out to be 0. So, when R e was very small, we did analysis for flow past a sphere, and we got C d is inversely proportional to Reynolds number, which matched experiments. Now, at the limit of R e becoming infinity, you get a flow field, looks like a flow field, but gives you 0 forces. Apart from your personal experience, you also have data C d versus R e. As R e becomes larger and larger, you have a finite value of the drag coefficient. Drag coefficient, in fact, drag scales with velocity square. So, if velocity is going to infinity, you expect drag to become very, very, very large. Instead, this result gives you forces equal to 0 and is certainly deserving of an explanation. We will see that with a little bit of correction, potential theory will continue to predict finite forces acting on the cylinder. Those corrections we will start discussing from after your, I should say, celebrations this weekend. So, till then let the result haunt you. Okay, now let us look at another example. Okay, so now I will also request you to fill in all the intermediate steps, carry out the integration, so show that forces are 0. With phi specified, find psi, plot stream lines that are constant psi lines, see how they look, not right away, later. Right away, I want you to focus on a slightly modified potential, which is u minus gamma over 2 pi theta. Now, I can throw any potential at you. Will you accept it? You will first check if del square phi is 0. Okay? So, a function of r theta or x and y is a valid potential only if del square phi is 0. Similarly, in 3D, you will still have to check, instead of del cross u dot k, that is what we have done to carry out calculations in 2 dimensions, but del cross u is still vorticity, and del cross u equal to 0 will give vorticity vector equal to 0, okay, and vorticity will be equal to gradient of phi. So, del square phi is still 0 in 3D also. So, the analysis carries over in 3D, but we are doing it in 2 dimensions. Now, I have given you a modified potential. Please confirm separately that del square phi is 0. The first part is the same as the previous example. We have added a term minus gamma over 2 pi theta. Question is, what does it represent? A quick way of interpreting the potential is to examine the velocity components. So, here u r will be u 1 minus r square over r square cos theta, just differentiating with respect to r, and the second term is does not have any r, and u theta will be u 1 plus r square over r square sin theta with a negative sign, that is the first term, minus the second term will be derivative with theta divided by r. This is u theta. Okay. So, on see, because of the appearance of capital R, there is a cylinder of radius r, and anyway this is a minor variation of flow past a cylinder. So, you can examine the velocity components on r equal to capital R. You find u r is 0. So, you still have flow past a circular cylinder. So, also notice that as r approaches, that means the radial distance approaches infinity, what happens to u r and u theta here? What happens to u r and u theta as r approaches infinity? They both go to 0, not 0, they both go to uniform flow. The second term gamma over 2 pi theta dies as 1 over r. So, as r approaches infinity, it has no influence far away. So, you are left with as r approaches infinity, u r is u cos theta, u theta is minus u sin theta, which is uniform flow. So, it is still uniform flow approaching a cylinder. And there is a cylinder of radius r, because on r equal to capital R, u r is 0. And how about u theta? It is minus 2 u sin theta, which is the contribution of the main flow. This main flow goes around the cylinder, minus gamma over 2 pi r. This gamma over 2 pi, gamma is a constant, a positive constant. So, let us write here. It is a parameter of the flow field. So, the second term is a constant, and if u theta is constant, it represents u theta is constant. What does it represent? Rotation of the object. The body is in continuous rotation with an angular velocity omega. So, and what is the sign of that angular velocity? You can see u theta is negative. So, the second term is negative. So, it represents clockwise rotation of the cylinder with an angular speed omega, which is equal to u theta divided by capital R, which is gamma over 2 pi r square. So, this slightly altered potential now represents flow past a circular cylinder, where the cylinder is given rotation omega. So, now we can find forces acting on the cylinder. So, P r theta divided by rho. I am now evaluating wall pressure directly, plus u r square plus u theta square divided by 2 is equal to P infinity over rho plus capital U square over 2. So, from this we can find P r theta, P so, on r equal to capital R, u r, the radial velocity component is 0, only u theta survives. So, let me divide just to maintain consistency with the previous calculation. It is equal to I am sorry, this 2 should be inside. So, if gamma is 0, you get back the previous result, that pressure variation is 1 minus 4 sin square theta. If gamma is not 0, this is the expanded form. So, now let us proceed to the forces. This x is equal to these are you know how to find forces, right, from pressure. Take a small element, multiply pressure by the small area, then take the component and integrate over the surface of the object. So, now you have to carry out that integration. The second term, gamma over 2 pi u r, is a constant, it is independent of theta. So, you just have to integrate the terms involving theta. It's a simple integration. So, here x continues to be 0 and y turns out to be a very important result, which is rho u gamma. So, the lift acting on this is a non-zero value. So, if you have a spinning cylinder, suppose omega, you increase omega, what is the relationship between omega and gamma? It is a linear relationship, right. Omega is equal to gamma over 2 pi r square. So, as omega increases, gamma increases. So, as you increase omega, this lift also increases. As you increase approach velocity u, capital Y increases. As density decreases, Y also. Why am I thinking of density decreasing? Because clearly x and y are lift and drag. Y would be lift and x is drag. Lift and drag acting on an object. And if you think of going to high altitudes, density is decreasing. So, as density decreases, lift also decreases. What are the units of rho u gamma? X and y. Look at P is multiplied by linear dimension r. So, these are in units of Newton per meter. So, how do you find gamma? For that you need omega. You are given omega, you can find gamma as 2 pi r square omega. And what are the units of omega? Radians per second. So, now you can ask, for once I have a result where the force is non-zero, is it correct? So, here I am happy to inform you that this result for lift, so maybe it is time to change the font color, there is a pen color. So, the first advantage of studying potential theory is it helps you determine lift. So, for lift calculations potential theory can be used, that is the first observation. But drag is 0, you flow past a cylinder and at high speeds drag is turning out to be 0, which is a disastrous result. But I gave you a hint that with a little bit of tuning of the pressure field, it is possible to obtain results for non-zero drag. So, we proceed to looking at the reason for the discrepancy. So, here incorrect. So, if somebody tells you the forces are correct or incorrect, if they are correct, it tells you that pressure distribution is correct. If it is incorrect, if force is incorrect, it tells you that the pressure distribution is incorrect. That is why you got a wrong answer. So, that is why it is good to examine the pressure distribution. So, let us start with the first example. In the first example, we had flow over a flat plate, where phi was equal to capital U x and we got u equal to capital V u, v equal to 0. So, P x at y equal to 0, this is the wall pressure divided by rho plus u square plus v square over 2 is equal to P infinity over rho plus capital U square over 2, which tells us that P infinity over rho. So, whatever pressure prevails upstream is distributed over this flat plate. So, the same P infinity prevails over the flat plate. Okay, so, that was the example of flow over a flat plate. Now, at high Reynolds number, does this result match experiments? See, it is in the vertical direction. So, you know the lift result was correct. So, this result is also correct for flow over a flat plate. You take a flat plate, how do you create? One possibility is have a moving object, that is harder to do. If you have a fixed object, then you have to blow air. We discussed quite some time ago that such experiments are carried out in wind tunnels, water tunnels. So, you have let us say a wind tunnel where speed is very high, viscosity is very small, plate length is substantial, you are going to get high Reynolds number, you measure pressure distribution, it will turn out to be nearly constant, practically constant. So, this result is experimentally validated. Let us look at the second example of flow over a fixed circular cylinder. So, now we are distinguishing between a fixed cylinder and a rotating cylinder. So, the first example was fixed cylinder. And on the surface of the cylinder, we got u r equal to 0 and u theta equal to minus 2 u sin theta. Hence, you remember the result p r theta minus p infinity divided by half rho u square was 1 minus 4 sin square theta at theta equal to 0. This is theta equal to 0, right. At theta equal to 0, that is point A. Let us say this is point B. Theta equal to 0, this P is, this pressure ratio is, let us call it P tilde equal to 1 and theta equal to pi, which is point B. P tilde is again equal to 1. If you consider some point C, which is theta equal to pi over 2, P tilde is equal to minus 3. Incidentally, this pressure ratio is also called a pressure coefficient in the book. Pressure coefficient. So, in line with drag coefficient, what is the symbol for drag coefficient? CD is the symbol for drag coefficient. For lift, what is the drag coefficient? Lift coefficient is CL. So, what should be the symbol for pressure coefficient? Cp, right? There is no surprise over there. So, Cp, and this Cp is a function of theta. So, if you plot for flow past a circular cylinder, this is theta, this is Cp. At theta equal to 0, it is 1, and at theta equal to pi, again it is 1, and at theta equal to pi over 2, it is minus 3. So, this variation is a sine square theta variation. I think I have drawn it, it is not very accurate, but this is the kind of variation. Is this variation right or not? Right meaning, is it's certainly right as far as the governing equations del square phi equal to 0 is concerned, but it does not match experiments. Okay. So, from an experimental angle or from an application angle, this pressure distribution is erroneous, and on Monday we start looking at how erroneous it is and how it can be corrected.